two-dimensional waves. We're focusing on the simplest case of a membrane, perfectly flexible membrane. It's uniform. Two-dimensional membrane. And it's characterized by some mass per unit area. That's rho sub s. And this is this kind of weird quantity, the tension per unit length that I described to you yesterday. That's the appropriate quantity here for the stiffness. This characterizes the inertia. This characterizes the stiffness. And we derived, it's essentially the derivation of a string, but just duplicated in two perpendicular directions. We derive this, and this is the standard two-dimensional wave equation. It looks just like, here's the one-dimensional wave equation, and just has another second derivative, but in that perpendicular direction. And you can probably guess what's going to happen in 3 dimensions. Anybody want to guess? Yeah. So we're going to get the partial 2 derivatives in the, well, we've got a coordinate problem. We'll get 2 derivatives in the y direction, okay? And that's what we're going to find is appropriate for sound in fluids. We then looked at, and we write, the partial with respect to x squared plus partial with respect to z squared as this Laplacian operator here, and it'll get generalized to 3 dimensions next quarter. And we focused on standing waves. So these are the normal modes. These are monofrequency responses of the system. There's just a single frequency here, right? And we have an infinite number of solutions, but they are complete and they'll describe any motion of the membrane if you superpose them. To hunt for these normal modes, normal standing wave modes, we use the usual form here, standing wave form, and we get, this eliminates time from the equation, and we get what's called the Helmholtz equation. And this k here is simply omega over c, right? And at this point, we don't know what the modes look like. We don't know what the frequencies are. We have to specify the boundary conditions. And so we need to solve this in general, and we use this standard technique here for partial differential equations is to assume a separable solution. So this psi here can be written as just a function of x times just a function of z, and that's justified at the end because we end up, all the solutions we end up with here, and here are the solutions. Now this is for a particular case of a rectangular membrane that's fixed around the perimeter. You have to specify, to get these normal modes, you have to specify the boundary conditions. So this is what we get. And if you change the boundary condition, these will change. And we'll do problems on that tomorrow, right? We have 2 problem sets on this chapter, but just 1 quiz. So because we're nearing the end of the quarter, I'll send out the quiz not long after the discussion tomorrow. So unfortunately, you'll have 2 quizzes at the same time. That's okay. Don't panic. It's just I'm giving you plenty of time to work on the final quiz here. And remember, I'm going to drop the lowest quiz score. So you don't have to turn in a quiz if you don't want to. So anyway, this is the solution, sort of the simplest first case where we have a rectangular membrane and it's fixed around the perimeter. Here are the waveforms, and they're sinusoids with half integral number, I can't use the word wavelengths here. They're in either of the 2 directions, you have half a sinusoid, 1 sinusoid, 3 halves of a sinusoid, etc. It's just like a string. It's just like a string in the 2 perpendicular directions. So you can imagine, most people, you can imagine a string here. And in the case of a string, it would be an integral number of half wavelengths, as we know. That's going to be any of those is going to be a mode. And here we have the same thing in the perpendicular direction. And here's the frequency. Now remember, this is just one, we multiply these, we don't add them. There's just one frequency here. This is the solution, and here's the frequency. We found the frequency. And often when you do experiments or theory, you want to be able to identify modes in ascending order. And you have to just calculate these. The order in which these occur, all these modes here, labeled by these two integers, these m and n, okay? And they start off at 1, 1, n equals 1, m equals 1. You have to calculate these frequencies to know what the ordering is. There's no formula that will tell you how to do that. And we have this nice picture here. This is a standard picture of it visualizing what's going on, where we draw the nodes here. Okay. So now we're going to do something much more practical, and that's a circular membrane. And this has applications, measurement microphones. The higher quality microphones are almost always have a membrane in there. It's really a capacitor. We're going to talk more about this next week, but a lot more in the transducers course. So there's a membrane here that's fixed on the perimeter, and that's what we're going to do. We're going to do the problem where it's fixed here. We'll do another problem in the homework, okay? And a sound comes and excites this membrane. And it's the membrane forms one plate of a capacitor, and then there's another fixed plate here. So a sound wave changes the capacitance here, and the charge is kept constant, so the voltage changes. So we'll get into this in the transducers course. But anyway, I just want to mention to you, this is one application of these modes of a membrane. Another one's, of course, musically, right? Drums, timpanis, or timpani, also called kettle drums, right? You guys seen those? So that's another musical applications here. Musical acoustics. All right, so here's the problem. We have this uniform membrane. It's stretched. It's under some uniform tension. It's fixed around the perimeter. We'll call the radius, typically we use lowercase a here to denote a radius. And we want to use polar coordinates here because we have to impose this boundary condition. And you want to use, this corresponds to a constant r equals a. So here is the wave equation in polar coordinates. And this is the same. But this is based, what's happened here is that the Laplacian, this is what it becomes, as I mentioned yesterday. When you transform from rectangular coordinates, you get this. And it's more complicated now. We have this linear term, linear derivative, and we have r's appearing. We didn't have x's and z's appearing before explicitly. It was just differentiating with respect to them. So it's more complicated now. So we're going to look for normal modes again. So it's the same kind of procedure as before, just we expect more complication. But it's a lot more interesting, and it's a lot more practical. You know, when people, if you want to do acoustics in an enclosure, do you want to build a box? Has anyone ever built a box? It's trouble. I did it once for a science project in like elementary school, and I'll never forget it. It was just a lot of trouble. So what we usually do is we get like PVC pipe and block off the ends, right? We have an enclosure. It's really easy. So this cylindrical geometry is very common. It's very common. And in fact, next quarter we'll be doing an experiment with this. When I first taught this course, we doubled up. We did an experiment with the circular enclosure, acoustics experiment. So this is air, sound modes in air inside a cylindrical enclosure, right? We also did a box. We have the boxes here somewhere. I haven't seen them for a while. And it took I think we spread it out over 2 weeks. But the problem was that the box was just kind of boring. The modes are kind of boring. So these modes are much more interesting. And it's much more practical, this geometry. So we dropped the rectangular box experiment. But we'll be doing this next quarter, an experiment of sound modes. It's a cylinder with some height that's not big. We want to really focus on the modes going in this way and not on the pipe modes. You know, if I have a cylindrical enclosure here, I can get, because we have the wave equation, we're going to get essentially, we can get string modes here. And they're modes in sound, compressions and expansions. And they're not all that interesting. But so we focus mainly on here, but we do drive high enough frequency to excite the first excited mode here. So we'll be doing that next quarter. And that's important for you to know because everyone has trouble when they first see this theory. Okay, because we're going to be hit with Bessel functions. And nearly every student has trouble when they encounter Bessel functions. And I'll talk a little bit about this. But I want to make sure you understand here that we're going to be going through this again for sound. And we're going to be actually doing an experiment. Okay? So if you don't get it this time, you can get it the next time. So the procedure here is the same as before. We assume a separable solution. So here's our time dependence. We're looking for normal modes. The R and theta, we assume it's a product of, we assume the separability here. And again, that's justified at the end because it's, the functions that we're going to get are known to be complete. They are known to describe any possible excitation, in this case, any possible excitation of the membrane. It's going to be described by a superposition of the solutions we get. So you can actually just stare at this and do it in your head. I plugged this in and we're using the prime notation because capital R is just a function of R, capital theta is just a function of theta, so I can conveniently use these primes. And we get this, and then the whole idea of a separable solution extends to separating. There's a separation process here. It's continual separation to get at the solution here. I get this. Now I want to get, and now it's convenient to go to, I don't know if we did this yesterday, to one side of the equation. We'll take this side of the equation to be all the theta stuff. Anything that depends upon theta over here, and everything depends upon R over here. So you can see we're going to divide by capital R, capital theta. We did that yesterday, but we've got more work to do here. We've got this little r, this variable r. So it turns out you want to multiply through by r. And when you do that, you can achieve a separable, you can separate the equation here. All the theta dependence is on this side, all the r dependence is on this, little theta dependence is on this side, little r dependence is on this side. And now, what's the next step? You tell me. I'll give you a hint here. This can be at most a function of r, because there's no thetas in here of any kind, capital or lowercase, okay? And this is at most a function of theta. If I'm at a certain r here and this has a value and I change r, can its value change? No, because we don't have any, doesn't depend upon r over here. So we infer that each of these has to be equal to the same constant. We're going to call that constant m squared, and everybody in the world does. This is one thing that everybody in the world agrees upon, as far as I know. We're going to call this m squared, okay? And again, if you feel funny about this is all in retrospect. But if you feel funny about this, you can, m could be complex. If you're worried about just possibly being negative, you can do that. All right, so that's our separation constant. This is, this whole idea of separating just permeates this whole method here. This is the separation constant. So let's look at the simpler equation first. This equaling m squared gives us, well, we've seen that forever. This is the equation. If I think of this as time rather than space, this is the equation for simple harmonic motion. So we know the solutions here. And it's convenient here to go not to sine plus a cosine, but a cosine with a phase. So that's what, there's going to be, of course, some amplitude here. But more important for our purposes right now, we don't really care about amplitude, is the fact that we can have any kind of a phase constant here and be a solution of this equation. That's going to be important, as I will explain. Okay, the next step here is this, and this is not, usually it's not obvious here. If we start, here we are, here's our membrane fixed on the edge. If we start at any point here that has some value of theta, let's start at theta equals 0. Let's see, this is theta equals 0. Okay? And we have this function here, capital theta, it's a function of theta. If I go around once, what has to happen to the function theta? In other words, what if we have this function theta, if we go around once, that's 2 pi radians, what do we have to get? We have to get the same value, right? So, suppose m is 1/2. Just for example, let m be 1/2. I start here. I've got the cosine of 0. Oh, neglect gamma now. We're going to set the gamma equal to 0. I'm sorry, I should have said that. For our purpose right now, this is irrelevant. Just set this equal to 0. So I have the if at theta equals 0, when m is equal to 1/2, well, the cosine of 0 is 1, right? I go around 2 pi. What's the cosine of 2 pi divided by 2? It's -1, right? Because it's the cosine of pi, and the cosine of pi is -1. So it can't be 1/2. That's ruled out. And in fact, if you think about it, any fraction, the only thing that we can have here are integers. 0 is permissible, of course, right? And that's a very important special case, and we'll be doing that. But we have to have integers. Now, there can be negative integers here, but you don't get any new modes. You know, the m equals -1 is giving you the same mode as m is equal to 1, so we don't include those. Now, this may seem obvious to you that when you have a function and you go around once, you have to end up back at the function. But it doesn't happen in modern physics, okay, in quantum mechanics. There, the function is called the wave function. Maybe you've heard of that before. Have any of you guys had modern physics here yet?
We're right now.
Oh, okay. There's the possibility, because what can only be observed is the square of the wave, the square amplitude of the wave function. The m equals 1/2 is permissible. And in fact, if that weren't true, the universe can't exist. Specifically, you can't have molecules and atoms. Molecules and atoms would not exist. Okay, remember high school? Remember high school chemistry? Everybody remembers high school chemistry. Did you talk about the Pauli exclusion principle? Does that ring a bell? Maybe not. I don't know. Anyway, this is related to this, so it's really a big deal. You know, this thing that seems obvious to us here, quantum mechanically, we need those. That m equals 1/2, half integers is very important. So the fact that you can only put an electron in an atom can only be in one state. You can't have 2 electrons in the same state. That comes from this the wave function changing sign when you rotate it 360 degrees. And in fact, there's an analog, I don't know what this calls, there's a kind of demonstration of this. And it's more dramatic if you have like a cup of water or coffee. Okay, so I'm going to go around 360 degrees. How am I going to end up?
Same.
You'd think the same, right? And if I went like this, you'd be right. But that's boring. Okay? I'm keeping my hand, the rules here is you got to keep your hand horizontal. I go around once. Am I back to where I started from? No. I've got to go one more time. Now I'm back where I started from. This is an electron. It's analogous to an electron, to the wave function in quantum mechanics. So we've gotten way afield here. Pardon me?
I'm not sure what just happened exactly. You said you're not in the same place. Like,
Well, yeah. Don't you feel a little bit different going like this? Isn't this different than that?
right?
Yeah. So I go around once, and I'm not back to where I started from. I have to go around again. That's exactly what happens with electrons, with spin 1/2 particles.
I've never seen that before.
Yeah, I'm not surprised. It's a secret. Not many people know it. Okay, but I've been around for decades, and
That's spin right there.
I pick these things up. Okay, I picked this up when I was a graduate student, and I just don't forget. These are things, certain things, you don't forget when you're motivated, highly motivated. So I don't forget demos. This is a demo to me. So, all right. So that's simple. What about this? What about the left-hand side? This is going to be equal to m squared. So we multiply through the capital R, put everything on one side of the equation, and we get this. Anybody ever seen this before? This is a famous equation, and I should have written it down. It's called Bessel's equation. Because, and I'll tell you why. So it's called Bessel's equation. Except for the trivial solution, it can't be solved with any simple functions that we're all familiar with, right? Like simple algebraic functions, sines and cosines, exponentials. It doesn't possess a solution. So the solutions are called Bessel functions. It definitely has solutions, and you're going to be seeing them. And here's the properties of the solutions of that differential equation. This big R, this function of little r, which we call big R, is in general a sum of two functions. They're called Bessel functions of the first kind and second kind, technically, but not many people call them this because it's kind of boring. What they do is, but unfortunately this injects a little bit of confusion here. They call these are the simpler ones as I'll describe. They call these Bessel functions and these Neumann functions. So I don't know, I only know a little bit of the history here, but this is what people usually, when they're talking about a Bessel function, they're talking about these solutions. We need two sets of solutions here in general, but these Neumann functions here, they blow up at the origin. So do they arise in our case? That's a point. That's a point on the membrane. So it can't be infinite. So why do they have Neumann functions?
They're talking about last quarter if you had a problem that excluded the order.
Exactly. We could be doing a membrane. Here's one example. It's kind of weird, but we could be doing a membrane. It's like an annular membrane. It's excluded here. And it could be tied down. You can imagine tying it down here and tying it down here. It's kind of a coaxial membrane. We could be doing this, right? Then, guess what? When you want to solve this, what do you have to do? You got to include both the Bessel functions and the Neumann functions. But I don't think in this sequence we're going to have to deal with Neumann. In the acoustic sequence, I don't think they come up. But they do, in electromagnetic, they can come up. Okay? Question? Okay. So people tend not to use this. When we talk about Bessel functions, usually we mean the J's, not the Y's. So we're going to forget these, and I don't think they're going to, like I said, I don't think we're going to deal with them, at least in the acoustic sequence. Now, as I said, most students when they hit this are typically juniors or seniors, undergraduates, and they just flip out. They just, and I did the same thing. I think everybody does it. Maybe La Raza didn't. He's like the only person I ever met. He probably had no problem with him, okay? Professor La Raza, because he can be very mathematical. But it's, the problem is we get spoiled. In education, we're dealing with simpler systems where we have nice solutions. You know, we don't look at sometimes the more realistic problems where the solutions are more complicated. But this is just a function like any other function. And in fact, what they actually are, and we'll talk about this. Let me go ahead and show you this right here. If you look at here's a Bessel function. You can see that it's kind of sinusoidal, but the amplitude is decreasing. It's like a damped sinusoid. And in fact, when you get away from the origin, the Bessel functions asymptotically approach a damped sinusoid. The damping is 1 over the square root of of r, in our case r.
Is it the same as a sink?
Excuse me?
Is it the same as a sink? First. J01 is a sink.
What is it? What's the definition of a sink function? I forgot.
Sin x over x.
Okay, this is, I believe this is square root of x. You can look it up. I haven't checked for quite a while, but it'll be in the book.
It's like sink's best friend.
So it's the square root. It's damped by the square root of x. I'm pretty sure that's the case. The sinusoid there, you have to be careful about this. The sinusoid is, it's neither a sine nor a cosine, it's in between. There's a phase. There's a phase there. So one of the first things, incidentally, historically, I think there's an entire book on Bessel functions. Watson or something like, do you know this?
Luscombe's buddy.
Luscombe's buddy?
No, he has a buddy that worships that guy. It's one of the guys from the University of Chicago.
Who, is this Watson?
He's got it all memorized.
So yeah, so there is a book, an entire book based on Bessel functions. So Bessel functions, the properties have been beaten to death because they arise all the time in circular geometries, cylindrical geometries. Often you're going to end up with a Helmholtz type equation. You know, the Laplacian is always floating around, electrostatics, all kinds of systems, not just waves. And you're going to be dealing with Bessel function solutions. Okay, so they get one of the, and they have, you can look up the multitude of properties, and one of them is, as you get away from the origin here, they start to look like they asymptotically approach a damped sine or cosine, but there's a phase in there. But you can look this up. People have solved this. They've beaten them to death, believe me. All right, so let me see. I have extra notes here. So, you know, Bessel functions are something you get used to. And fortunately in acoustics, we can visualize them. You know, you'll be able to, you're going to be mapping out Bessel functions next quarter with a microphone, with a little microphone on the end of a tube going into this enclosure. So you'll be essentially seeing Bessel functions. One of my favorite examples is a water cooler, or what do they call it? You know, these 5-gallon or things of water, containers of water, where you, water cooler, they still call them a water cooler? I don't know.
Oh, like the ones they throw on the coach? Oh, okay.
What?
You know, at the end of the football game, they dump the...
Okay, now I'm talking about the kind that, you know, it's this giant bottle, and you turn it upside down, and you put it into an office water cooler.
Oh, I gotcha.
Yeah, not an NFL water cooler. Okay. So you have this spout, right? And you can take water. Everybody's probably done this. And somebody takes some water. Eventually, what's going to happen? A bubble comes up. What happens to the surface? Well, it looks usually pretty complicated. But if you wait a little while for all the higher modes to die out, what do you see? I'm looking for, it's a Bessel function, okay? Now it's not the Bessel functions, we have a fixed rim here. So it's not going to be, the water doesn't do that. Water is the other simple boundary condition. It's approximately, zero slope. It's like a free string. But you will see it's a beautiful Bessel function. Beautiful. Right? And it lasts typically a long time. After the other modes die out, it's going to be the low frequency mode. So we'll actually, I think we might solve that problem in the homework. I don't know, we'll see. But we'll definitely do it in acoustics because the free boundary condition is analogous to acoustics. Because we deal with the pressure, and the pressure is an antinode of this. If you're not getting this, don't worry about it. But we're going to see this again. We're going to see this again next quarter. So Bessel functions are real things. There's no, you don't need to be afraid of them. But I know everybody goes through this kind of fear of Bessel functions for a while. But it's nice in acoustics that we can visualize them. All right, so let's now get into the, how do we need to impose the boundary condition. Here it is. Well, here's our solution here. Remember, this m is the same m as before, called the azimuthal number. It dictates what's going on angularly when you go around in theta. We have to have this being 0. So the issue comes up. What are the zeros of the Bessel function? Well, you can't determine them analytically. They have to be determined numerically, except asymptotically. Once you get out here a ways, once you have a damped sine or cosine, we can find them. Anybody can find the roots of that, right? So they're known asymptotically. But in here where we typically live, you know, you need to look them up, and they're in the back of the book, and we'll be doing problems in this. So our condition here, this is going to give us our frequencies, because we have to have Ka being equal to 0, and this is going to have to equal to 0 of the Bessel function. And this is, as far as I know, universal notation. They use a little j, mn. This is the nth, this is the value along here, where you have, this is the nth root of jm. That's what this notation means here. So the meaning is, for example, here's J0, right? This is... these are, yeah?
Why isn't it not just the zeros when cosine would be 0, based on, like, if it's sine over something squared?
Square root. It is, but that's only asymptotically. So you have to be way away. So here's what.
How would that change?
Here's the problem. Let's look at just J0, and let's just go with most people go J0 of x, right? So it looks something like this. Okay. In here, these yeah, you got to be out here to get the asymptotics. This becomes the 1 over the square root, I believe, and you can look that up. So because we tend not to deal out here with out here, because we're typically close here, we just look them up and use the roots. Okay, so again here, for each j, J0, J1, and J2, etc., there are going to be they're going to be roots. So J0, here's the best, I think the best thing I can do right here is, here are the roots. So what's this? Okay, we're dealing with the m equals 0. So it's J0 of 1. This is J0 of 2. This is J0 of 3. Etc. And then if we looked at J1, and we'll look at J1 in a moment, it's going to similarly have zeros. So you can see those are important, because that's going to tell us what the spectrum is, because once we, let's see, Ka is equal to the root of a Bessel function. So that means, because this is a function of m, you know, these indices here, m and n, our km, and our frequencies, omega is equal to ck. So this gives us the frequencies, and here they are. Here are the frequencies, omega divided by 2 pi, and we're using omega is equal to ck. So you can see here, to get our frequencies, which are very important in acoustics, we got to know those zeros of the Bessel functions. So here's the full solution for the mn solution, and we denote it like this, just like we do with rectangular geometry. Oh, except we put the m first. There's a little bit of a distinction there. I just realized that. So usually when you do this, you want to, first of all, nail down what type of Bessel function it is, the m value. And then you go to whichever You know, there's going to be a frequency corresponding to these. So here's the solution. Here's the radial part being multiplied by the angular part, the azimuthal part. And we have an e to the I omega mnt. There can be a phase. I'm being very general here. There can be a phase here. Now, when you superpose these modes, each can have its own amplitude, right? And you can have this phase constant can be anything. And originally I had an m in there, but it gets tedious to carry that around, so I got rid of it. Okay, so now what we're gonna do now is look at various pictures of perspectives on Bessel functions. The first one here is just a graph. Now this is not complete for our purposes because we need to get the angular parting. We have this two-dimensional geometry, right? But this is a good place to start. We have, at r equals a, we've got to have 0. So here's the lowest frequency solution. It looks like this. This is going to correspond to the membrane doing this. Okay, you can see there's no nodes, no interior nodes. We just have a node at the rim here. And what's going, for J0, what's going on this way in our membrane when we go around? What's the variation? I have to draw this again. As I go around here, how does the amplitude of the membrane change? Right, because it's m equals 0. It has no angular dependence. Here. M is equal to 0. Theta is gone. So these are the azimuthally symmetric modes. And that's water cooler mode is azimuthally symmetric. So usually what happens after the other ones die out. So this is not the only, this is the n equals 1 solution. There'll be an n is equal to 2 solution, and that corresponds to the addition of another node. So there's a little bit of a problem here. When we start to superpose when we look at solutions corresponding to the different n's here, 1, 2, 3, they're getting all compressed. So you have to, it's different than what we often think of just plotting a function like that. You'll see here's the n is equal to 1. And that corresponds, our rim is right here. Okay? When I go to the next, when I go to the J0 corresponding to the next root, I compress this. It'll naturally be compressed in our argument right here. So here's what it looks like. So this is our physical point of view of the membrane. It's going to look like this right here. So now this is the, because we've changed the K value here, because we've got in a higher frequency, this is going through oscillations more quickly as you go from here to here. So focusing on the azimuthally symmetric modes, this is going to be the first one. The next one's going to look like this with one interior node, and the next one's going to look like this. And all this information is right in here. It's right in there. Okay, let's look at J for m is equal to 1, Bessel function for m is equal to 1. So what does m equals 1 mean? We have now we have an angular dependence, and what does it look like? When m is equal to 1, what does cosine theta look like? There's going to be, if we're going to call this theta equals 0, what's that going to be? What's theta of pi over 2? 0. Right? And similarly here. So we have a nodal diameter. We didn't have any, we couldn't have these before. Oops, I just realized. What's happening? Look at the n equals 2. What's happening here? It's a node, right? So we're going to see the visualization of that in a moment. But that's going to correspond to a nodal circle. Because at when r is equal to this value, no matter what theta is, you have 0 response of the membrane. So we'll see pictures of this in a moment. I want to point something out here. You'll notice J1 has a 0 here. Only J0 is not 0 at the origin. And you see how it has a slope here? So when you approach this, the J1s all become, for small r, they're proportional to r. What do you think J2s, what would be the simplest thing for J2s to do? They go like R squared. So J2s come in as a parabola down here. J3, it gets more and more of a, becomes more and more of a zero. And a higher order Bessel function is very peculiar. It looks like this. It has a strong zero here, you know, R to a very large power. So it just hugs the zero here, and then it kind of goes like this and then damps out. And that actually describes some physical phenomena. In fact, I wanted to tell you how Bessel functions came about, and very few people know this. I heard about it. I've never confirmed it. I just heard about it from a graduate student when I was a graduate student.
From another graduate student?
Yeah. Actually, he was an undergrad, but he was very sharp. And he went on to get a higher. So I've never confirmed this, but it just sounds true. It sounds too bizarre not to be true. What Bessel was interested in was not circular geometries. He was interested in the modes of a hanging chain. A hanging chain has modes. You can see them, right? There's going to be one that kind of goes like this with no node. The next one up is going to have a node. So you know it's going to look something like this, you know, going back and forth. There's no mass on the end here. There's no mass on the end. There's going to be one that looks like this. That's where there's one node there, etc. He wanted to find those modes. Do you think those are Bessel functions? They're not. He made a transformation. This is bizarre. He came up with a different, why is this a hard problem to solve? Can somebody tell me why this is hard? Can you imagine trying to solve this? What's the tension? The key is to look at the tension.
It's not uniform.
It's not uniform. It's inherently not uniform. If I just have a hanging string here, gravitational field, what's the tension down here? It's zero. It's not supporting anything. So the tension here is very small. Here's the tension's the maximum. And it's easy to show, Gene. It's easy to show that the tension is a linear function here. The tension as a function of x, if I call this x equals 0 and this L, the tension looks like this.
See the other way? Tensions.
Yes, thank you. The tension looks like this. And the tension here is just the total mass times g. So there's no way you can approximate that as a constant. So this leads to an equation which Bessel then he made a transformation of variable of x and perhaps the displacement, I don't know. And he ended up with what we now know as Bessel's equation, which is universally applied in circular geometries. But it does, I warned you, it does come up in other situations. And that's how it was discovered, apparently. Okay. So here is from Morse's book. This is a classic book on not just acoustics, but when he says vibration and sound here, we would translate this as 3119. Okay, so part of the book, roughly half of the book, is what we're doing in this course. So most acousticians own a copy of this. It's still in print. It's cheap. The Acoustical Society sells it paperback for nothing. So if you get serious about acoustics, or at least vibrations, stuff in this class, you want to get a copy here. This is 1936. Here's a three-dimensional view of the m equals 0, n is equal to 1. So there are no interior nodes, right? Here's our boundary. And the membrane is just doing this. Looks like that. And it has this axial symmetry here. If you look at a circle here, they all have the same instantaneous value of the displacement from equilibrium. It's best now to move, I don't know how he came up with this order. It's best to look over here. What's happened here? So this is the m equals 0, n is equal to 1. When we increment n by 2, we're not going to get a nodal circle. So you can see that's the dashed line here. We get a nodal circle, okay? And we can do it one more time. Now we get 2 nodal circles for n is equal to 3. And if you keep incrementing this, you can go to infinity and you just get more and more nodal circles. They just get crammed in there. As mutually, here's the m equals 1 mode, n is equal to 1. So there are no nodal circles here, because n is equal to 1, but we have 1 nodal diameter. And where can that nodal diameter can be anywhere. It depends upon the initial conditions, and we'll talk about that in a moment. Let's move on to here now. Here we've, this mode is interesting because now we have both a nodal diameter and a nodal circle. And it's starting to get hard to see, right? But they're there. And then this one is just impossible. You can stare at that if you want to.
Professor?
Yes.
So when you said like in a water cooler, the higher modes amp out, then you just get a beautiful looking Bessel function. Which one does that look like then? Is that the any
Okay. This has a different boundary condition. It's fixed. The water cooler is free. That makes a big change in things, and I'm going to talk about that in a moment. Okay. So just hold off. We'll talk about the water cooler in a moment. Here is the standard. This is like what we did with the rectangular. Here's the standard representation, looking down on the membrane. Now, instead of using plus or minus now, that doesn't seem good. It's because it gets a little complicated here. I'm going to shade it. So you can shade either section here. The point is, any point here is 180 degrees out of phase with a point there. So this is a nodal diameter. So it could be going like this. It's positive here, it's going to be negative all the way out here, right? And then half a cycle later, it's flipped. So this will be below. So this conveys the information. And something remarkable happens here, and it's deceptively simple, okay? It turns out the ordering of the frequencies is like this. So this is the lowest frequency mode, the fundamental, which is very reasonable. This is the next mode up, okay? And then you might think, well, maybe this is the next one up. It's all in the math. What you find is when you substitute in the Bessel roots, this is the next one up, okay? Now these modes will just keep on going. You keep adding a nodal diameter. That's what we're doing here. We're incrementing m here. But the next one in frequency turns out to be this one. And then the next one after that is this one, this one, this one, this one, and this one. And you wouldn't know that. It's not at all obvious. You need to look at the math. I mean, you can see that this is going to have a higher frequency than something like this, because you can see kind of a wavelength in here. It's hard to see the wavelength here. You really have to calculate it. But there's a kind of characteristic wavelength here, and it's a lot smaller than it is here. So you know this is going to be higher frequency. But when it gets to distinguishing this, you can make an argument here. This is like one wavelength across here, roughly, whereas this is a half a wavelength. So you can actually bet money that this is going to be a lower frequency than that, and you'd be right, okay? Now, in the problem set we're going to talk about, that's where we really should bring up the water cooler modes, because we're going to do the problem. I think we're going to redo this. I remember this was 4 years ago. I think we're going to go through the solution here for the free boundary condition. So maybe it's best to wait till then, and we're also running out of time. So we'll do this tomorrow, okay? We'll talk about the water cooler mode some more. Now, we're not done yet. Wait a minute. I've drawn this node here, but it doesn't have to be there, right? If I have a drum head or a timpani head, and let's say I strike it here, I hit it here, I'm going to excite a bunch of modes. One of them is going to be the 1-1 mode. What's it going to look like here? I hit it here. Well, it's going to have a nodal diameter there, right? Because I've hit it there. Now, there'll be other modes, but this will be one of the modes for sure. What if I hit it here?
entropy.
Right. It's going to be, you know what it's going to be if you consider this diameter here and you go perpendicular to it. That's what's going to be excited. So it would depend upon initial conditions. We can take this one step further. This is the last thing we're going to do here. So what I just said is this will be what happens if I hit it here, right? Here, I'm hitting it here or here, doesn't matter, here or here, right? That's all for uniform tension. We talked a little bit yesterday about what happens when you don't have uniform tension. So suppose this is some kind of drum head and it's tightened more here. So this is supposed to denote a greater tension along these in this direction right here compared to the rest of it. Now, what happens if I hit it here? Well, I'm going to have a nodal line like this, right? Fine. What happens if I hit it here? Well, I'm going to have a nodal line like that. But the important thing to realize here is those frequencies aren't going to be the same because of the non-uniform tension. In this mode, this is going to be going up and down, and it's because of that greater stiffness there, it's going to tend to have a greater frequency. What about this one here? Well, the greater tension is near the node. So this mode is not going to, it's going to be exploring a little bit of the greater tension, but it's not as much as that. So when we have a uniform tension, all of these have the same frequency, but that they're degenerate. All of these modes here, just by changing the diameter, the location of the nodal diameter is not going to change the frequency. However, when you have a non-uniform membrane like that, now we don't have all these solutions. The two solutions are going to look like this. There's going to be one with a nodal diameter. Remember, these are normal modes, definite frequency. One of them is going to be with a nodal diameter here, and one of them is going to be here. This one will have a slightly higher frequency than that one. We say the degeneracy has been lifted. These are degenerate. They all have the same frequency. But a little bit of non-uniformity here will lift that degeneracy. So if you hit the drum here, the timpani or whatever. Drums, it's hard to hear a pitch, but a timpani has a definite pitch, right? If you hit it here, you're going to hear something. You hit it here, what's going to happen? It's going to be a little lower. And our hearing is good, by the way. We can hear, in pitch, we can hear frequency differences of about 0.5%. It's actually quite remarkable. So it doesn't take much here for you to be able to hear the difference. And that, musically, that's probably a bad thing, right? If you've got a timpani that hasn't been uniformly tensioned, now they can change the tension while they play, right? There's a foot pedal and there's a rim here, but it changes it all the same all the way around. You've got to start off with it uniform tension, uniform tightening of those screws, because otherwise you're going to get different pitches at different locations. Although that might be a good thing. And I'm almost willing to bet, I'm not a betting person, but I'm almost willing to bet that some culture at some time had non-uniform, drums go way back, right? You know, they're going to go back tens of thousands of years. Maybe the problem is that they have evidence of flutes, right? I think, I might have mentioned this to you guys, over 40,000 years ago, they found flutes. Good. So maybe some culture has actually intentionally gone to a non-uniform tensioning in order to get slightly different frequencies for whatever purpose.
Steel drum.
To prevent it from raining or to get rain when it's dry. Of course there's a connection, right? Beat on a drum, and I'm just kind of joking, right? But that's the way it was, right? Not very scientific. Pardon me?
Great dance.
Yeah. Okay, all right. So problems tomorrow.